We are now going to use the example of rabbits reproducing to explain exponential growth. Suppose that there is a community of rabbits with a starting population of 60 rabbits. And suppose that the rabbits will also always reproduce at a rate of that is 1/30th the amount of rabbits that there currently are. So for example, there's 60 rabbits. In the first month, there would be 1/30th of that many rabbits reproduced. 1/30th of 60 is 2. So they'd be reproducing at a rate of 2 rabbits per month in the first month. In the second month, there'd be more than 60 rabbits now. So they'd still be reproducing at a rate of 1/30th per month, but the rate would increase. This may not seem like many rabbits, considering in the first month only 2 rabbits are reproduced. So they are only gaining 2 rabbits per month in the first month. That is their current rate. But what if we wanted to know how many rabbits there would be after, say, 10 years? So we're not asking the question of only what's their reproduction rate, but how many rabbits there actually are in 10 years. This gets to the heart of differential equations and exponential growth. We're given a rate and we want to figure out an amount. That is differential equations in a nutshell, and this really encapsulates exponential growth when we're talking about rabbit reproduction. We could calculate the rate of reproduction after 10 years. In other words, we could just keep multiplying our amount by 1/30th, adding it, and then taking 1/30th of that, but we're going to get decimals. It's going to be very difficult to compute by hand. The best way to do it is to use calculus. We've already looked at separable differential equations in this class. Now we're going to use them to figure out how many rabbits we'll actually have after 10 years. So to represent this using a differential equation, the rate in which the population is changing is equal to 1/30th of the amount present. This can be explained in this sentence right here. Rabbits are increasing is always 1/30th of the current population. So let's say somewhere down the line we have 300 rabbits now. 1/30th that would be 10 in that particular month. We'd be increasing the population at a rate of 10 rabbits per month. So you can see again it's like a snowball effect. The more rabbits there are, the faster the reproduction rate is. Which makes sense, right? Because in nature you have more rabbits that have sex with each other, therefore there's going to be more rabbits. Converting a few things in the formula, I'm going to pull the p up to the top and put the 30 on the bottom, and then we will convert p prime of t into dp dt. So the rate in which the rabbit population is increasing is equal to 1/30th of the population. Now we're going to do some math. Now we can solve the separable differential equation. So again, to solve a separable differential equation, you're going to get all of the dt's on one side and the t's on one side, and you're going to get all the p's and the dp's on the other. So I'm going to multiply both sides by dt, and then I want to take this p and move it to the left. So in order to do that, I'm going to multiply both sides by 1 over p, or you could also say divide both sides by p. When I do that, the p's right here are going to cancel, and I'm going to be left with 1/30th dt on the right and 1 over p dp on the left. So now I have all of my dp's on one side and my dt's on the other. There is no t in this equation because the rate of increase is constant. However, I have separated my dt's from my p's and dp's. Now what I'm going to do is integrate both sides. Remember, if two things are equal, then their antiderivatives are equal. We know from previous lessons that the integral or antiderivative of 1 over p is the natural log of p. And on the right, we have a constant, so the antiderivative of that is 1 over 30t. Don't forget your plus c. Remember, your plus c always goes with your independent variable. Now we want to get p by itself because we want to figure out the population of rabbits after 10 years. So we're going to raise both sides of the equation. We're going to make both sides of the equation the exponent of e. What that will in effect do is cancel this natural log, and now we just have p by itself, which is what we wanted to begin with. Now we have p is equal to e to the 1/30th t plus c. Now we want to figure out what this c value is, otherwise we will not be able to figure out how many rabbits there are after 10 years. In order to do that, what we will do is notice that we have two variables in the exponent, or two terms. We have a 1/30th t, which I will denote in purple, and we have a c. Remember that when you have an exponent which is a sum, you can break it down into a product. So this will become e to the 1/30th t times e to the c. Okay, so here's our first part and here's our second part. Now, if that doesn't make sense to you, imagine if we were to multiply these like bases, we would add the exponents and we would end up with 1/30th t plus c, which we started with. So the reverse is obviously true. We've talked about before that you take any arbitrary constant and you just make it c. So for example, e to the c is still just a constant since e is a constant and c is a constant. So I'm just going to change that to c. Finally, what I'm going to do is take the c and move it out front. So now we have our population of rabbits is equal to a constant number times e to the 1/30th t. Take note that that 1/30th is still in the equation. If you remember correctly, that 1/30th represents the fact that that is the rate in which the rabbit population is increasing is equal to 1/30th of the current amount. And since we know there were 60 rabbits starting out in the community, we can use this initial value. P of 0, time being the 0th month, is 60. So we're going to plug in a 60 for P, and we're going to plug in a 0 for T, and now we can solve for C. Now the exponent is going to become 0, so it's going to be C e to the 0, but e to the 0 is 1, which makes C, our C value, equal to 60. Here is another thing you might notice. Our initial population of rabbits shows up right next to our E. Now, as we derive the formula for exponential equations, I want you to notice those two things. The initial population goes first, and the rate is the coefficient of the variable in the exponent. And that will always be the case, and I will do a proof of that later on to explain further. Note the presence of the growth constant. So that number that we just showed right here is the growth constant, and it will always be that number that's to the left of the variable. And again, we can denote as you will use the letter K to denote the growth constant, and you can see where it showed up in the initial differential equation. The rate in which the population of the rabbits was increasing is equal to 1/30th of the current population. We will now change this fraction to a decimal, so now we have the population. The actual population of rabbits at any given time is equal to 60, which is the initial population, times e to the 0.033, repeating t. So we can plug in any number now in for t, and that's the only variable we have on the right, and that will give us the population on the left of the rabbits. So now let's answer the question, how many rabbits will there be after 10 years? Now, if you recall, the rate in which the population of rabbits increases is 1/30th of the current population, and that rate is given in rabbits per month. That was given to us in the original problem. Since it's rabbits per month, we have to convert 10 years to months. So therefore there are 120 months, and therefore t will be 120. So we're going to plug in 120 into our equation right here. Plug that into a calculator and solve, so you get 60 times e to the whatever that is, and we get 3,276. Now again, this is the initial, this is the population equation, not the rate. So this actually tells us how many bunnies we have after 10 years. Again, this gets to the heart of exponential growth. We started out with 60 bunnies, and every month the rate in which the bunnies was increasing was equal to 1/30th of the population. After 10 years, all of a sudden we have 3,276 bunnies just from starting population of 60. So there would be 3,276 bunnies hopping around after 10 years. Now suppose we were given any growth rate in any initial population and wanted to have a formula for the population at a given time. So let's talk about money like we did before, right? Or any kind of amount in general that has to do with the fact that the rate in which it's increasing or decreasing is proportional to the amount that's in there. This is how we would do it. Now I'm going to show a formal proof later, but for now I'll just explain it this way. This is called the exponential differential equation. As you can see, this is a direct proportion. So the rate in which the population or the amount is increasing is directly proportional to the current population or amount. So that's what dPdt means, and P means the population. Again, K is the growth constant, as you can see in this formula right now. Previously with the bunnies, we said the growth constant was 1/30th. If you have a positive K, that indicates exponential growth. If you have a negative K, that indicates exponential decay, which happens with carbon, fossils, and that kind of thing. The equation literally reads the rate in which the population is increasing is proportional to the actual population. So here is our exponential growth equation. The P naught represents, in our particular example, the 60 rabbits. We showed that initial population will show up as this number right here. So I'm even going to notate that. Now it's not always 60, but in our example it was 60. This number right here, K, represents the growth constant. In our particular case, it was 1/30th. It can change depending on the particular application. E will always be your base, which I find interesting, considering that the rate in which it's increasing is proportional to this constant number. But we already showed the math behind that, and showed that when you use calculus and integrate, you do indeed end up with an E in the equation. So moving on, T represents time. Now, if the rate was bunnies per year, then T would be in years. So that T can change depending on the particular problem or application. All of that will give you P of T or A of T, which is your population or your amount after a certain amount of time. So given that rate, you can easily deduce every time that it's the initial population or initial amount times e to the kt, where k is your growth constant. Keep in mind that exponential growth increases without bound as time goes on, and exponential decay, growth decreases without time as growth decreases without bound as time goes on. The final thing I want to do is relate this to interest, compound interest. We can take this same formula and write it in terms of compound interest. You might have seen this formula before. A equals P e to the RT. Almost exactly the same thing as we were just showing, except instead of talking about population, we just use A to represent the amount in the account. Instead of talking about an initial population, we use P to represent the principal. E stays the same in the formula. R is actually the growth constant, but in the compound interest formula, R represents the interest rate of the particular account that you have it in. It's the same as the growth constant, and T remains T. So that's it for explaining exponential growth in terms of rabbits reproducing at a rate of 1/30th of the current population. If you have any other questions about this, let me know.